Okay, so what we have here is a picture of ice, water, and steam, or looking at water in its solid state, in its liquid state, and in its, we would say, gaseous state. So how do you have an ice cube turn into liquid water? You add heat and it will melt. How do you have liquid water turn into steam or gaseous water? You add heat, right? You can pretend there's a little flame here. You add heat and it will boil or vaporize. Is the term we actually prefer. So to go from a solid to a liquid to a gas, what we see happening as we add heat is the phase changing. Now, if you look down on a molecular level, this again represents solid, liquid, and gas, but we can see what's happening to the molecules here. So we know that we're adding heat in order to get that ice cube to melt or that water to boil. But what you can see is that each, say, molecule of water, when it's a solid, any solid, they're packed really closely together, and you don't see much movement in the molecules themselves. Some, but not much. In a liquid, those molecules have then been broken apart a little bit. They're still connected as liquid. If you look at a cup of water, you just still see one conglomerate of water. But the molecules themselves actually have a little more distance between them and are moving a little faster. And then as a gas, they're moving way faster. The molecules are way further spread apart. So why does adding heat do this? Well, remember that what holds one molecule to another molecule into these aggregates that we can actually see are the IMFs, the intermolecular forces. So for water, we know that if we drew out water and looked at its Lewis structure, you would see that it's polar and has hydrogen bonds. That means there are hydrogen bonds existing in between every molecule of water in this picture. If we add enough heat, we get those molecules to move a little bit more, and eventually they're going to be able to overcome some of that IMF, some of those hydrogen bonds in this case that are holding them together. If you think of it as the intermolecular force, that force being overcome, being weakened, boom, then we can have those molecules spread apart once they overcome that force. So when we talk about a substance's melting point, we're looking at, well, at what temperature, how hot do we have to get it before enough of those bonds are, not bonds, sorry, enough of the intermolecular force has been overcome that we now have a liquid instead of a solid. When we're talking about a boiling point, it's the same idea. We're saying, how hot do we have to get something before it can vaporize? So the stronger the IMF, the better held together the solid or the liquid is, the harder it's going to be to overcome that force. And so the higher the melting point is going to be and the higher the boiling point is going to be. So a higher melting point and a higher boiling point correlates to a stronger intermolecular force. It can be confusing. Sometimes MP means melting point, like in this shorthand I use down here. Sometimes on past assignments, you'll see it means molecular polar, like we've drawn out the Lewis structure and decided it's polar. So just use context to help you there. Now, a couple examples, what we can do with this information. Frankly, it's not much different than last lesson, just that tidbit that a stronger IMF gives you a higher melting point or a higher boiling point. So if we want between two molecules like calcium oxide and hydrogen to decide which has a higher boiling point, we need to decide what intermolecular force holds them together. And in order to decide that, we need to classify the type of crystal. So you practiced that last lesson, but calcium's a metal, oxygen's a nonmetal. Since we have a metal and a nonmetal, this is ionic, which means that it's held together by ionic bonds. H2, well, hydrogen is both a nonmetal, so I could draw out its Lewis structure to see if it's polar or not polar, but the fact that it is some kind of molecular, it ends up being nonpolar, frankly, and you should know that of all diatomics, that they're nonpolar. That tells me we have London dispersion forces holding it together, which we know are not going to be as strong as ionics. So ionic, stronger, higher melting or boiling point, regardless of what the question asked. If we're asked to rank a bunch, again, let's start by classifying all the types of crystals. So lithium is a metal, oxygen's a nonmetal, therefore this is ionic. Leave it there for now. Boron and hydrogen are both nonmetals, so this is molecular. And I'll have to draw it out to know if it's polar or not. I'm going to draw it quickly from my memory. You would have to actually draw its Lewis structure for real, make sure everyone's happy, count all the electrons. What I can see here is that it is nonpolar because all of the atoms attached are hydrogen, and there are no lone pairs on the boron. Remember, boron's one of our exceptions that's happy with 6. So since it's nonpolar, we're dealing with just some London dispersion forces. Water, maybe you know if we've done it in enough examples, but maybe not. They're both nonmetals, so again, we're dealing with something molecular. Drawing it out to know if it's polar or not polar. We can see the lone pairs on the oxygen. Lone pairs on the central atom make it polar, but also since we have a hydrogen that's bonded to an oxygen, FO or N, we know that we have a molecular polar with H bonds, hydrogen bonds. So therefore we have hydrogen bonds here. Switching colors again, sorry, I should have done that more. Magnesium is a metal, sulfur is a nonmetal, so we're dealing with something ionic. And then carbon, hydrogen, and chlorine are all nonmetals, so it's molecular. Since it's molecular, I have to draw it out. Again, I'm being quick with my Lewis structures, but you want to make sure you can draw it out accurately. That is polar because not all of the atoms attached to the carbon are the same element, and therefore we have dipole-dipole forces. So all of that work that I showed is the type of work you'd want to show on today's try problems. Now, if you know the order of strongest to weakest IMFs, we know the order of highest to lowest melting points. So all of these, we know that, let's see, we don't have any network covalence. That's the strongest. So those would be the highest melting points. But ionic would be next. And we have 2 ionics. So Ms. Prater talked about how to choose between 2 ionics in a video last class. There's also a video from last class that talks about how to choose between 2 molecular nonpolars if you need to review those. Here for lithium, we're looking at a +1 and oxygen's a -2. For magnesium, we're looking at a +2 and sulfur's a -2. Sorry, that's not a 2. So the +2, -2, those are bigger charges than the +1, -2. That makes it stronger. So, and I'm going to give myself a little bit more space here. Since the MgS has these stronger charges, that is how we know it's the stronger IMF, and that would be the highest melting point, would be MgS. Coming right before that would be my other ionic, lithium oxide. So I've dealt with those 2. And I'm writing my answer up here. Remember, we want the highest melting point. If we're going from lowest to highest, we want the highest melting point listed last and the lowest melting point listed first. So weakest to strongest IMF. After ionic, I'm working my way backwards. After ionic, the next strongest intermolecular force would be hydrogen bonds. We only have 1 here with hydrogen bonds. Again, sorry, it was super messy, but water has hydrogen bonds. We can't give you 2 different ones with hydrogen bonds and ask you to rank them. After hydrogen bonds would be anything with dipole forces. That would be this one. So CH3Cl. And then we have a molecular nonpolar. That must be our lowest melting point. Again, if I gave you 2 molecular nonpolars, Ms. Prater showed you how to figure out between those which is higher or lower. So this would be our answer. And let us know if you have any questions.